Okay, now we have started our lecture officially. Okay, so our last meeting was 2 weeks ago. It's been quite some time. But if you remember what we were discussing in our last lecture, basically, so far I tried to summarize what a controls engineer do. Okay, and I don't know if you can read these, but what you see here summarizes a controls engineer's responsibilities. Okay, so I'm a controls engineer, and my entire life is filled with these things. Okay, so these are the things that I do professionally. So first, I consider a system, and then I need to obtain a mathematical model for that system. For certain times, you'll be given the mathematical model, but for other times, you will have to be it will be your responsibility to make that model. So writing the physical equations to represent a system is a part of our responsibility, obtaining the equations for a system. And then once we have that mathematical model, then we use it for two main purposes. One of them is system analysis, the other is control synthesis. And in the system analysis, we basically take the model and then consider a certain input to our system, and then using the model we calculate what the response of the system will be to that input, or the output of the system. And in the second part, control synthesis, in fact this is the more fun part, I guess. In this part we have a target output. Okay, so we want the system to have a certain output, and then to reach that desired output we try to find a suitable input to the system. So that's the second part. So in this course we will be doing the system analysis in the most the biggest part of the course will be devoted to system analysis. But now we will continue with writing the equations of the system part. Okay. So today I would like to start from here, mathematical modeling of physical systems. So to write the equations, you need to know the physics of the system, right? So whatever system you are trying to model, you need to know the physics of that system, basically. So we can consider mechanical systems. We can consider electrical systems. There are other types of systems like fluid systems and thermal systems. And for each one of these systems, there are physics involved, and you need to know those physics to be able to write the equations. So let's start with the mechanical systems. So these are systems that we mostly deal with. As aerospace engineers, chances are you will also mostly be working with mechanical systems. So this is the part that I will. So this is, I guess, the most important part among all these different types of systems. For example, if you are in an electrical engineering department, then obviously you would consider electrical systems more. So that's another thing. This controls engineering is can be studied under many different departments. In the world, mostly electrical engineers and mechanical engineers study controls. But in many universities like ours, aerospace engineering also studies controls as well. But apart from these classical engineering departments that work control systems, there are departments like chemistry. So in many universities, in chemistry departments, you see controls related courses, because control is a big part of their work as well. So they try to control chemical reactions, and they use the same type of controls theory that we teach here. Also in some universities under biology departments, people work controls engineering. And in some universities, controls engineering is a separate department, like Istanbul Technical University. They have a separate controls engineering department. So the entire department only works with controls engineering. Okay, so let's start with these mechanical systems. So whenever you are to model a physical system, you have to first recognize the elements involved in that system. Okay, so if you are talking about mechanical systems, then the elements are the following. First, we have inertial elements. So basically these are, so let me use this so that you can follow. So the inertial elements are the object with masses and moments of inertia, and they store potential and kinetic energy. Okay, so whenever you have a mass, that's an inertial element. That's what we call it. They store potential and kinetic energy, right? So if you have a mass and it is at a certain height, then there will be a potential energy associated with that. Or if it's moving with respect to some fixed reference, then you can talk about the kinetic energy associated with that motion. And if this mass is rotating, then there will be rotational energy involved, right? And we call this the rotational kinetic energy. And this time, not mass, but the moment of inertia will be important. Okay? So it depends on where, with respect to what axis you are rotating this element. So for example, if you have, here there's this circular object, and if you are rotating it with respect to its center, then there will be a moment of inertia and associated kinetic energy with that. But if you are rotating it with respect to an axis that is somewhere here, so this, now imagine that this entire object is rotating with respect to this point, then the moment of inertia will be different, right? And you know how to calculate these from your physics courses. Okay, so the inertial elements are really probably the most important parts for mechanical system, because whenever you have an inertia, then you have an energy storage element. Okay, so now this is the important part for us. So when you have an inertial element, and there is an external force or moment acting on this inertial element, there will be a motion, right? So if you have an inertial element here, and you apply a force to it, then there will be, this mass will start moving. And we know that this phenomena is governed by the Newton's laws of motion. So you can write this equation to study the motion of this element. So if you want to track the motion of this object, first you have to define its position with respect to some coordinate system. So let me call this y-axis. So this is a fixed reference. And if a force F is acting on this system, there will be an acceleration, and we can write this as F is equal to m times a, where a is the second time derivative of this position, y. And right now we have a differential equation, right? So for this simple system where there is just one inertial element and an external force, we already have a differential equation. So if you remember our discussions before, so we can immediately say that this is a dynamic system because we have a differential equation representing its motion. So remember, for dynamic systems, differential equations are involved. And if you have a non-differential equation, then that makes it a static system. Okay? And then the next type of elements we consider are the spring elements. So this is how we represent the spring elements graphically, and in reality springs look similar to these, right? Usually springs work in both directions. That means a spring has a neutral position, a neutral shape, and if you change the distance between the two ends of a spring, you get a force. So if you compress the spring, then you get a restoring force. That means the spring force tries to push it backwards. But if you extend the spring, then again it tries to go back to its neutral shape. In that case, the spring force will be in the opposite direction. You're also all familiar with springs, right? And the spring equation is a static equation. So we write the spring force as a function of the displacement. Here, y represents the deflection from its neutral shape. Okay, so if for this spring the neutral shape is, so this is the neutral length of the spring, and if you extend the spring, so this pen I'm using is not really working properly. That's why I have trouble writing and drawing here. Okay, so this is neutral position, and if you extend the spring, in this case there will be a force in this direction, and the magnitude of the force will be equal to some constant that we call y, k times y, and y here is this distance. And similarly, if the spring is under compression, this time the spring will be pushing on that end. And this time y is this distance here. So anyway, this is the equation for a spring, right? F is equal to some k times y. And as you can see, this is a static element, right? Because the equation is not a differential equation. Okay, so the springs are static elements. So if you make a plot of the relation between the spring force and the deflection, so let this be the spring force and this is the deflection. So force is equal to k times y, right? So that makes a straight line. So how much deflection you apply to it, you get a force proportional to that deflection. So this graph is a straight line, which means that the spring is a linear element because the input-output relation is in the form of a straight line. Okay, so that's how you recognize a linear system by looking at its graph. So this is the ideal case when k is a constant number. Okay, but in reality, all springs have some nonlinearities, right? So you deflect it with a certain amount, you get a force. You deflect it more, you get more force. But after a while, the force deflection relation departs from this straight line. So for some cases, you get a relation like this. So you apply more deflection, but the spring force doesn't increase by the same amount. So these are called softening springs. So it's already written here. So these are softening springs. But in some other types of springs, as you apply more deflection, the spring gets harder or stiffer, which means the spring force increases more rapidly. So this green one corresponds to a stiffening spring. And if you want to model these green or red ones, so for the black one, which is a linear spring, the relation is F is equal to some k times y, and k is a constant number. But for the green and red ones, you can still use the same equation, but you should recognize that that spring constant is not a constant number anymore. Okay. And for the green one, we have the same thing. And if you remember what I said about linear and nonlinear systems, in linear systems, all the system variables should appear alone. So if you have a y term or a y dot term or y double dot term, they should all appear by themselves without any other dependent terms on y. But in this case, you have this y dependent k, and this definitely means that this is a nonlinear spring. And so is this, obviously. Okay, so far we said we have inertial elements, and then we use spring elements. The third element type we use for modeling mechanical systems is the damper element. So these elements dissipate energy in the form of heat, and they apply a force proportional to speed. So if you go back to springs, here we have a force that is proportional to position. So the spring force is proportional to the deflection. But for the dampers, they are similar to springs in a way, but instead of the position, the speed is important. So they create a force that is proportional to how fast the two ends of the damper are moving. So for dampers, we use this symbol. So let's say we have a fixed reference here. And so this is how we denote a damper. And if we call this Y again, damper creates a force whenever Y is changing. So if we have a damper for which the time derivative of y is positive, so y dot is bigger than 0. So what does that mean? That means the damper is moving in that direction. So in this case, at the end of the damper, there will be a force in that direction, and that is going to be proportional to speed. So the discussion we just had about springs can be repeated for dampers, but this time we can use the same graph. So let me just copy this entire thing. But this time the horizontal axis should be y dot. Okay, and then to prevent confusion, we use a different letters, usually B. Okay, so if you have, so I shouldn't forget the dots here, so there should be a dot here. There should be a dot here. So the reason we use this symbol to represent the damper is dampers in reality look like that, right? So here's here in these pictures, the inner workings of a damper are shown. So the basic dampers are most of the time composed of a piston moving inside the cylinder, and the piston is filled with a fluid. And if you move the piston within the tube, the fluid will be escaping from one side to the other side, creating a flow here. And due to the viscous friction there, you get a resistive force. Okay, and this friction depends on the velocity. So if you move the piston slowly, then the flow here will be slow and the reaction will be less. But if you try to move it fast, then there will be a faster flow around the piston, and that will create more resistance, and that's how you get a bigger reaction force. Okay? And then there are rotational versions of these elements, like for the spring and damper. You can talk about rotational spring and rotational damper. They are very similar to the linear versions. But for the rotational spring, the spring force depends on the rotation angle. Instead of the displacement, the spring force depends on the rotational deflection. So let me try to draw a rotational spring. So if you have two elements like that, if you have a rotational spring, you can show it like this, for example. Okay? So if you move this part to here, for example, that there will be a force proportional to this angle here. So in this case, the rotational torque is going to be proportional to that theta. So this is a rotational spring. And similarly, if you have a rotational damper, it's going to have this equation. The torque is proportional to the first time derivative of the angle. Okay, so believe it or not, but these elements are sufficient to model any mechanical system you can imagine. So mechanical system can be a very simple system with just one mass and that's it. Or you can have a very complex system such as, I don't know, a huge aircraft or a system with many masses connected together. So even the most complex mechanical system you can imagine can be modeled by using these three elements only. So I'm going to show you some examples of that today. Well, in reality, in certain cases you have these actual elements, like you have a real spring connected or a real damper, so you can immediately write the equation for that. But in certain cases, these elements are used to model certain properties of materials. So I don't have one here, but imagine a rubber ball, for example, right? The ball has a mass, right? So you can, that's an inertial element. But if you squeeze a rubber ball, its shape will change, right? It has some elastic properties. So to model that flexibility of a rubber ball, you can use these spring and damper elements. So in that case, there's no real physical spring element or a damper element, but the properties of the rubber exhibit these behaviors. So you can if you imagine a rubber ball, as you squeeze it, if you want to squeeze it more, you need to apply a greater force, right? So if you apply a little force, it will be squeezed just a little. But if you apply a greater force, you can squeeze it more. And if you increase the force, its deformation will be stronger, which means it has a behavior just like this graph here, right? You apply more force, you get more deformation. So that's how you model flexibility. So, for example, in that case, there is no actual spring and no actual damper, but you still use these equations and these elements to model a flexible element. So here you see this strategy to model a mechanical system. So when you have a mathematical system you want to model, first you identify the inertial elements. Well, you need to identify all the elements, and then you determine the forces and moments acting on these elements. So that's the next step. And then you write the equations between the forces and the motion of these elements. And for that you have two options. You either use the Newton's second law of motion to write the system differential equations, or you can use work, energy and power methods. So you basically consider the energies. You write the potential energies and the kinetic energies in your system, and then you get the equations for your system through that approach. Obviously, in the end, you get the same model. So for the same system, you get the same equations, but you can follow two different approaches. Okay, so that's how you model mechanical systems. So you have three main elements, and then you need to know the forces, obviously. So for example, if you want to model an aircraft, obviously you need to model the aerodynamic forces, because the motion depends on the aerodynamic forces like the lift force, drag force, the aerodynamic moments, and that's an important part of the modeling process. You need to model those forces, and then you can write the equations for your aircraft. Okay, so let's start with this simple example, spring mass damper system. And let's see how we use these elements and these approach to actually obtain the equations for a sample system. Okay, so this is perhaps the simplest mechanical system you can think of. You have just one inertial element with a certain mass, and it can move through a single axis only. So it can go back and forth along this horizontal axis. And this means that there is no friction. So whenever you see such a symbol, you can assume that there is no friction force. Because there are these wheels and it can slide back and forth freely on some rails. So this is our coordinate system. So we express the motion, the position along this axis with variable y. Okay, and there may be an external force applied to this system. So we don't know what this F is, but that is applied externally. Okay, so you can have, for example, a propeller here. So that propeller can be applying, creating a force, or you can have some magnetic ways of creating a force on that object. So we don't care what that is. It's just an F for us. And there are these spring and damper elements attached to this mass. So depending on the position, there will be a spring force and depending on the motion, there will be a damper force. Okay. So when writing the equations, obviously we need to be careful about the variables you are using. So for mass, for example, in the SI unit system, we use kilogram for mass, and for position we use again the metric system. So we can present position in terms of meters. The force in this case should have a unit of newtons. The spring constant has a unit of newtons per meters because it's about a force proportional to deflection. And for dampers, the unit is newtons per meters per second. Okay, so here it says we have one inertial element that can move along one axis only. This means we need to write the Newton's second law of motion just once. So before we can write this equation, we need to determine all the forces acting on this mass element, right? So we know that there's this F force, and then there may be spring and damper forces depending on Y and Y dot. So this is the critical part actually. So in most students have trouble writing these spring and damper forces. There's really nothing difficult about that though. You have to be careful about how we determine your coordinate system. Okay. So first you start with setting up your coordinate system. So in this case we assume that so if we choose this as our positive y-axis, so the y specifies the position of this block with respect to some fixed reference here. So this is our y. So to write the spring and damper forces, it is best if you just assume constant an instant where y has a positive value, and also y dot has a positive value. Okay, so this is just an assumption we make. We consider the forces acting on the mass at an instant where both y is greater than 0 and y dot is greater than 0. Okay, so after making this assumption and specifying the direction of the y, it will be very easy to write these forces, right? So we know that there is an external force. Let me just write that immediately. And since y has a positive value, and remember y is equal to 0 corresponds to the case where the spring is in its neutral shape. Okay, so when y is equal to 0, spring doesn't have any force. But when y is greater than 0, that means the mass is so the mass has moved to the right, because y is greater than 0, in which case the spring will be extended like that. So in which direction will the spring force be acting? Towards left or towards right? Towards left, right? It's very easy to see that. And y dot is also positive, which means at this instant the mass is actually moving towards right. Okay? And in this case, the damper force will be also acting on towards left. So this is going to be spring force, and this is the damper force. And we know that this should be equal to some constant times the deflection. So let these be the spring and damper constant, and the damper force will be proportional to y dot. Okay, so these are all the forces acting on this mass. So now we can write the Newton's equation. So the total forces acting on this mass are equal to, if we choose this direction to be positive, so we have F acting in the positive direction, but then we have the spring force acting in the opposite direction, so I should use a negative sign there, K times Y. And then similarly the damper force is acting on the other direction, so that should be also negative. So these are the total forces, and this should be equal to the mass of that block times its acceleration. So, and that's y double dot on the right hand side. So now this is the equation for this simple mechanical system. Okay. So if this is our system, right? So let's consider what's happening using these system representation. So we should have inputs and outputs to this system, right? So can you tell me what is the input here and what is the output? That's right, this force is our input. So this is the input to the system, and the output can be chosen as the position, for example. So we can consider y as the output, or alternatively we can also consider the speed as the output. So if we are interested in how fast the block moves, we can use y dot as our output. So these are both valid outputs for this system. Okay? And again, the equation for this system is the following. So let me write it one more time. So y double dot is equal to 1 over m times Okay, so usually it becomes easier to write system equation in this form. You leave the highest order derivative in your equation alone, and then you write everything else on the other side. In this case, y double dot becomes equal to 1 over m times these things. Okay? So I would like to show you some more examples of modeling mechanical systems, but the idea will always be the same. So obviously when you have more complex systems, the things get more complicated. But I think the most difficult part is this part. So you need to be careful about how your elements are moving. So if the spring and damper forces, you should be careful about determining the direction of your forces. Other than that, everything will be just straightforward. Okay, so let me just stop here and let's give a 10 minutes break and continue after that.